Hi, it's Mr. Mac, and we're looking at dynamics and the third inquiry question to do with momentum, energy, and simple systems. And the inquiry question is, how is the motion of objects in a simple system dependent on the interaction between these objects? We're learning to analyse quantitatively collisions of objects by their momentum, impulse, and kinetic energy. And we'll be able to analyse quantitatively the interactions between objects in a simple system. Here are the NISA content outcomes for this part of the course, and I'll leave those for you to look at in your own time. So let's start with the question, what is momentum? And just think of how difficult it is to stop a moving object. You might want to take some time to watch the Looney Tunes coyote running after the roadrunner, but being chased by a steam locomotive, and see how hard it is to stop a moving object. But it also is the converse. How difficult is it to make a stationary object move? The answer to both these questions depends on two physical characteristics of the object. Firstly, the mass of the object, m, and secondly, how fast the object was moving, or how fast you want to make it move, v. The product of these two quantities is called momentum, and momentum is given by P equals mv. Please note, P is a vector and V is a vector. Also note, P has no relationship to the word momentum, but we need to learn that this is the variable that is used for momentum. Momentum is a vector quantity and has SI units, kilograms, meters per second. Well, let's derive the impulse momentum equation. Suppose you apply a constant net force, F net, to an object of mass m. Newton's second law tells you that the object will accelerate if it starts with initial velocity u. After some time t, its velocity will be v. And here's a diagram to show that. The acceleration of an object equals its change in velocity divided by the time it takes the velocity to change. So from the kinetics equation of motion, we have A equals v minus u all on t. If we multiply both sides of this equation by t, we have at on the left equals v minus u. And now if we multiply both sides by m, we have mat equals m brackets v minus u. Now note carefully that ma on the left is the same as f net, or sigma f. And if we multiply out the brackets, we now have sigma ft equals mv minus mu, which is delta p. That's the impulse momentum equation. We're going to use the impulse momentum equation to look at collisions, which looks at motion of objects in simple systems, and asking the question, how is the motion of objects in a simple system dependent on the interaction between the objects? Well, there's a way to explore this, and you can watch inelastic and elastic collisions and write a summary paragraph of the two types of collisions. You can click on the link here, and if that doesn't work, then go to the PDF and click on the link there. There's also a collision lab that works if you can run Flash on your computer, and then you can watch some crazy snooker shots just for fun. And now it's time to look at a worked example of inelastic collisions. Consider an inelastic collision between two empty freight wagons, shown here as red and green, both with a mass of 22 tons. What is the new velocity after they link and roll together? And the data is m1 is 22,000 kilograms, m2 is 22,000 kilograms, both SI units. The initial velocity of 1 is 10 meters per second, and the initial velocity of the green is 0 meters per second, and we want to work out their combined velocity after they link together. So from the formula sheet, we have sigma mv before equals sigma mv after. I think it's best to learn this helpful formula, which is the same thing using very easy symbols. So m1u1 plus m2u2 equals m1v1 plus m2v2. So simply substituting mechanically, 22,000 times 10 plus 22,000 times 0 on the left-hand side equals 22,000 times V plus 22,000 times V. Notice that the V in this case, because they're linked together, is the same velocity. Simply doing the calculation, 220,000 on the left equals 44,000 V on the right, and dividing we have V equals 5 meters per second to the left. Is that reasonable? Well, let's have a think. The momentum before and after the collision is the same. The kinetic energy, however, is less after the collision than before the collision. Why is that? What's become of the energy? Well, let's look at an elastic collision where the kinetic energy does not change into heat energy. So momentum is conserved, and in this case, kinetic energy is also conserved. In the diagram on the right-hand side, the picture you'll see is Antares, a 10 megavolt tandem accelerator, which is run by the Australian Nuclear Science and Technology Organisation, ANSTO. So here's the example. In a particle accelerator, a proton collides with a second proton in a head-on elastic collision. The first proton has a velocity of 1.3 times 10 to the 6 meters per second to the right, and the second proton has a velocity of 2.5 times 10 to the 5 meters per second to the right. Calculate the speeds of the two protons after the collision. Please note down the bottom of the page, MP is given in the data sheet. So the data we have is M1 equals M2 equals MP, the mass of a proton. U1 is 1.3 times 10 to the 6 meters per second. U2 equals 2.5 times 10 to the 5 meters per second. And we want to find the velocity of both protons after the elastic collision. From the formula sheet, sigma mv before equals sigma mv after. But remember this, m1u1 plus m2u2 equals m1v1 plus m2v2. Substitute mechanically, mp for the mass of the proton times 1.6 times 10 to the 6 plus mp times 2.5 times 10 to the 5 equals mpv1 plus mpv2. Multiplying out what we know using a calculator, 1,550,000 equals v1 plus v2, and dividing by mp, which is common on both sides. But wait a minute, there are two unknowns here, v1 and v2. So how do we solve this problem? Well, we need to look at the law of conservation of energy since it's an elastic collision. And so because it's an elastic collision, we know the law of conservation of momentum, u1 minus v1 equals v2 minus u2. Just check that. Remember, we've deleted mass of a proton from both sides of the equation. But the law of conservation of energy says sigma a half mv squared before equals sigma half mv squared after. And again, let's use a similar expansion, which means half m1 u1 squared plus a half m2 u2 squared equals a half m1 v1 squared plus a half m2 v2 squared. Again, dividing by mp on both sides since it's a common factor, and also multiplying by 2 to get rid of the halves, we see that u1 squared plus u2 squared equals v1 squared plus v2 squared. And let's swap sides and see what happens with proton 1 on the left and proton 2 on the right. Both the difference of two squares. We can factorize. And look at the top. We can substitute the u1 minus v1 for v2 minus u2. That's the only change we've made. And then cancel out what's common to both sides, which is the v2 minus u2. And we're left with u1 plus v1 equals v2 plus u2. Rearranging to find v1 and using the law of conservation of momentum, replacing u1 with v2 minus u2 plus v1, we end up with 2v1 equals 2u2, or simply put, v1 equals u2. and by similar reasoning, V2 equals U1. So the two protons have swapped velocities. Whatever was the velocity of the first proton, the second proton has that velocity. And whatever was initially the velocity of the second proton, the first proton has that velocity. Now, before we get to two-dimensional momentum, I want you to complete exercise set 10 on elastic collisions. And when you've done that, you can watch the 2D momentum example from the YouTube clip and write a summary paragraph of what you see from that example. And think, what are some other examples of 2D collisions, and then write down a list of those examples. I'm Mr. Mac. Thanks for listening.